Hi everyone, my name is Argyris Oikonomou, and this is a talk about computing simple mechanisms left and round over marginal reduced forms. This is a joint work with my advisor, Yang Zhao, and Mingfei Zhao, who is now at Google Research. The focus of this talk will be on combinatorial auctions. In this setting, there is a seller who wants to sell M items to N buyers. The goal of the seller is to maximize her revenue. For example, the seller could manage a convenience store and wants to sell fruits to buyers. For each item, each buyer has a type that encodes how much she values that specific item and each subset of item she might receive. For instance, if the buyer's valuation is additive, then her type for an item is just how much she values this specific item. We assume that the type that each buyer has for the items is sampled from distribution. Throughout this talk, we are going to assume that the type that the buyer has for different items is independent. That is, her type is sampled from a product distribution. This is also known as the item independence assumption. The goal of the seller is to elicit buyer's preference over outcomes using a mechanism. A mechanism consists of two steps. In the first step, buyers report their type to the mechanism. Observe that buyers can misreport their type to the mechanism. In the second step, the seller decides the outcome and how much each buyer pays. Throughout this talk, we assume that all the mechanisms we consider satisfy two properties. The first property is that the mechanisms are Bayesian and setting compatible, which means that in expectation over the other buyer's bids, it is the best interest of a buyer to report her true type to the mechanism. The second property is that mechanisms are individual rational. That is, each buyer is not better off by not participating in the mechanism. An example of a mechanism is a two-part tariff. In a two-part tariff, buyers arrive sequentially and in an arbitrary order. The seller sets prices for the items. The prices are the same for all buyers. Each buyer can see the set of remaining items and is allowed to purchase her favorite bundle if she pays a personalized entry fee. The seller only knows the distribution that each buyer's type is sampled from and not their realized type. Moreover, this mechanism is dominant strategy incentive compatible, which means that it is in the best interest of the buyer to report truthfully regardless of what the other buyers are doing. The problem we are going to focus is the following. When can we efficiently compute a mechanism with approximately optimal revenue under the item independence assumption? Before proceeding any further, I would like to take some time and provide some motivation and background for the problem we consider. First of all, mechanism design for arbitrary distribution is well understood, and algorithms for computation of mechanisms with approximately optimal revenue in time polynomial in the support of distribution are known. However, arbitrary distributions are uncommon. On the other hand, item independence can be considered as a natural and popular class of structured buyer distribution. Unfortunately, optimal mechanisms are known to be intractable even for a single additive or unit demand buyer under item independence. Moreover, under item independence, algorithms for arbitrary distributions run in time polynomial in the support of the buyers, which is exponential in the natural description of the problem, as they are agnostic to the structure of the buyer distributions. So the question is whether we can compute approximately optimal mechanisms in polynomial time. A recent line of works on mechanism design studies the trade-off between the optimal revenue and the revenue of simple mechanisms. A mechanism can be considered simple if there is a straightforward interaction between buyers and the seller. Several works use the item-independent structure and were able to show that simple mechanisms can have approximately optimal revenue for several classes of buyer's valuation beyond additive or unit demand. However, Most of the results are existential, and algorithms for computing such simple mechanisms are only known for additive and unit demand buyers, or when buyers are symmetric. So, one natural question is whether we can use these existential results for computational purposes. We answered this question in the affirmative, as these existential results are the building block for the computation of our mechanism. Now, I would like to provide a brief overview of the way that we model Bayes valuations. Arguably, among the most classic classes of Bayes valuation are the classes of unit demand and additive valuations. When a buyer is unit demand, her value for a group of items is only her value for her favorite item in that group. When a buyer is additive, her value for a group of items is just the sum of the values for each individual item. A famous class that contains the additive and unit demand valuations as special cases is a class of constrained additive valuations. High-levelly speaking, if a buyer's valuation is constrained additive, it is additive over constraints over downwards closed visibility sets. For example, if you're on a diet, your set of visibility constraints is any combination of foods with 2,000 calories or less. You just want to maximize your happiness factor from eating with respect to your calorie budget. The final class we consider is the class of XOS valuations. The class of XOS valuations contains a class of constrained additive valuations. If you are not familiar with what an XOS buyer is, I would like you to think about the class of constrained additive instead. All the results of this talk are about constrained additive or XOS valuations. As I have mentioned earlier, under item independence, simple mechanisms are known to approximate the optimal revenue within a constant factor for multiple buyers with valuations as general as XOS. On the other hand, under item independence, efficient mechanisms with approximately optimal revenue are not known for buyers beyond the class of additive or unit demands, regardless of simplicity. Our work can be thought as trying to catch up the constructive with the existential results. Now, we are ready to present our results. We showed that under the item independence assumption, and when we have access to Bayes distribution with valuations as general as constrained additive, then we can efficiently compute a mechanism with expected revenue and constant fraction of the optimal one. Moreover, we assume we have access to a value oracle. A value oracle takes as input a type of a buyer and a set of items, and outputs the value that the buyer with type T has for this set of items. Moreover, we assume access to a demand oracle. A demand oracle takes as input a set of prices and a buyer's type, and outputs the buyer's favorite bundle. When we only have sample access to the Bayes distribution, we have an extra additive error in the revenue, and the running time of our algorithm is also polynomial in the inverse of the additive error. Finally, we saw how to extend the results to XOS buyers. When Bayes valuations are XOS, we assume access to the standard value oracle and a generalization of the demand oracle, the adjustable demand oracle. The adjustable demand oracle is a stronger and more general oracle than the demand oracle. I'm not going to provide a definition here. Please look at our paper for more details. Moreover, we showed that we cannot simulate the adjustable demand oracle having only access to a demand oracle. We leave it as an open problem whether we can compute approximately optimal mechanisms for XOS buyers using the demand oracle rather than the adjustable demand oracle. I would like to note again that algorithms for arbitrary distribution need exponential time in the natural description of the problem to compute an approximately optimal mechanism under the item independence, or resolve achieve an exponential speedup. Moreover, our computing mechanism has a very simple structure. It is either a two-part tariff that we mentioned before, or a positive price mechanism. In a positive price mechanism, buyers arrive sequentially and in an arbitrary order. Each buyer is presented with a personalized price menu and can purchase at most one item. Similar to the two-part tariff, the seller only notes distribution of buyer's type and not their realized type. Similar to the two-part tariff, this mechanism is also dominant front and incentive compatible, which means that it is always the best interest of the agent to report truthfully, regardless of what the other buyers are doing. Now, we are ready to present a high-level technical overview of our approach. For simplicity, the overview will be about constrained additive rather than XOS buyers. The ideas and technique extend to XOS buyers. The starting point of our algorithm is the existential result by Zhao and Zhao, who showed that simple mechanisms have revenue within a constant factor of the optimal one for constrained additive valuations. More specifically, they showed that for a mechanism M, there exists a set of dual parameters theta such that the revenue of the mechanism M can be bounded by a constant times the revenue of the optimal positive price mechanism and the function of the mechanism and the dual parameters, the core. Those who are familiar with the core-tail decomposition, core can be viewed as a welfare truncated under dual parameters theta. If you are not familiar with the core-tail decomposition, you should think of core as a benchmark of the revenue of the mechanism, which we can bound using the revenue of simple mechanisms. Moreover, an immediate consequence of their analysis is that we can compute a two-part tariff with a revenue at least a constant fraction of core. Our goal is to make their existential results constructive. A well-known way to represent mechanisms is through the interim allocation form. I'm going to talk more about interim allocations later. Ideally, we want to approximately optimize core over interim allocations. Unfortunately, core is not concave in the interim allocation, and it is unclear how to efficiently optimize over them. Moreover, we need exponential space in the natural description of the problem to store the interim allocations. The rest of the talk are going to show how to convexify the core and how to store succinctly the mechanisms. First, I would like to present an abridged description of our approach. In the existing approach, we need to search over exponentially many pairs of mechanisms represented by their interim allocations and dual parameters in order to find the maximum value of the core. In our approach, we show how to succinctly store mechanisms that we maximize the expected value of the core over distributions of dual parameters and mechanisms, which might include in its support a pair of mechanisms and dual parameter whose core cannot be bounded by simple mechanisms. To deal with this issue, we saw how to robustify the analysis by Zhao and Zhao to be able to bound expected core by simple mechanisms. As we mentioned before, the existing results for each interim allocation can identify a set of dual parameters theta, which enable us to compute a two-part tariff with revenue a constant fraction of the corresponding core. In our approach, we first fix a set of dual parameters theta, and we maximize the core over interim allocation sigma, so that the core of the dual parameter and the interim allocation can be bounded by the revenue of the two-part tariff. The first computational issue of our approach is storing the interim allocation. More specifically, for buyer I, the interim allocation is defined over the support of the buyer I. And the interim allocation of buyer I for item J with type Ti is the probability of buyer I receiving item J with type Ti. Observe that the interim allocation requires space proportional to the product of the support of buyer I for each item, which is exponential in the natural description of the problem. To overcome this obstacle, for each buyer I, item J, and type Tij that the buyer has for item J, we introduce the marginal reduced form representation, which is equal to the marginal probability that buyer I has type Tij for item J and receives that item. we define as the joint marginal reduced form polytope a set of marginal reduced form variables realized by some mechanism. One important property of the marginal reduced form is that it requires space proportional to the sum of the supports of buyers for the items. We are now ready to introduce our marginal reduced form relaxation. We express core with respect to the marginal reduced form variables instead of the atrium allocation, so we can succinctly search over mechanisms. Then, we relax the requirement for the marginal reduced form variables to be satisfied jointly. Instead, we require that the marginal reduced form constraints to be satisfied per buyer, and we introduce a supply constraint so that no item is over-allocated by the relaxation. Under this relaxation, we can ensure that the maximum value of core in the relaxed program can still be bounded by a two-part tariff. One more issue is that the constraints for buyer's margin reduced from polytope are implicit. One way to deal with this is to construct an explicit proxy polytope using the technique by Zhao, and Weinberg. One caveat of their approach is that their proxy polytope is within an additive approximation of the target polytope, which would lead to an additive approximation of the optimal revenue for our relaxation. To obtain multiplicative approximation of the value of the relaxation, we strengthen the results and show how to construct an explicit proxy polytope contained in the target polytope and that contains a constant fraction of the target polytope. We believe that this result might be of independent interest. To recap, given a set of dual parameters theta, we can optimize the core over a superset of mechanisms with dual set of parameters theta and still be able to bound a relaxed core by simple mechanisms. However, a set of dual parameters can be exponentially large, and our program does not have a clear structure that allows optimization. To convexify the program, we lift our program in a higher dimension and maximize the expected value of core over joint distributions of dual parameters and marginal reduced form variables. Due to the structure of core, our new lifted program has polynomial many variables, but might contain pair of dual parameters and mechanisms in its support whose core cannot be bounded by simple mechanisms. To overcome this final issue, we robustify the analysis by Zhao and show that we can still bound the expected core by a two-part tariff. Finally, I would like to conclude with two open problems. As I have mentioned before, our computational results for mechanism for XOS buyers requires access to an adjustable demand oracle. An interesting open question is whether we can still compute approximately optimal mechanisms using only the standard demand oracle. The second open problem is whether we can compute approximately optimal mechanism for a more general class of buyers valuations, the class of subadditive buyers, regardless of simplicity. Thank you for your time.